So what's up guys? In this video, I wanted to show you how we can do message handling, a proper message passing structure for the microcontroller. So the way we want to do this is by using what we call a message queue. As I explained in our previous video, we can perform simple message passing by just using a global variable and allowing it to be read between tasks. And as I stated, when you use a method like that, because it's an 8-bit microcontroller, it does provide atomic access for doing something like that. But it's not really a recommended approach. If you want to make our scheduler resemble more RTOS functionality, we need to implement a messaging system. And the way we'll do that is, of course, by using a queue. So we'll use our message queue, and the way we'll do it is by creating a circular buffer. We have our struct for the queue. It's like a typical queue data structure. We have the data, the head, and the tail. We have a queue of type message queue, and a message queue of type queue, sorry. We have an initialization for the message queue by setting the head and the tail indices to 0. And message queue is a global variable of type struct, and that will represent the message queue. This initialized message queue, init message queue function, will be responsible for setting the queue. We have the inQueue function, and what this function will do is to add a value to the message queue, and we assign the value to the element at the tail index. And if the tail index exceeds the queue size, we refer to the beginning of the array, and we accomplish this with the modulo operator. This is what really gives buffer the circular behavior we're looking for. Then we have the dequeue function that retrieves almost the oldest value from the message queue. So it assigns the value from the element to the head index, and then it increments the head index by 1. And if the head index exceeds the size of the maximum index, it wraps around to the beginning of the array using the modulus operator. So this inQ and DQ, this is our circular structure. Then we have, of course, a function for indicating if the queue is empty. So to implement this, use it. We have task 1, and what task 1 does is, task 1, in addition to blinking its LED, task 1 will put a value in the queue. And what task 2 will do is, task 2 will attempt to dequeue a message from the queue once there is a message. So once there's a message in the queue, task 2 will dequeue the message. And we don't need these counter variables anymore. We don't need any delay feature, because task 2 running will be solely dependent on task 1. So let's run this code, and let's look at the output. Look at the output, we'll see that the task 1 LED and task 2 LED both flash at the same rates. This is because the value that we are using for sending the message is once every 2 counts have elapsed, we'll toggle the LED on task 2. So if we, for example, change that to 20, and try again, now you can see that task 2 LED blinks that much slower because the rate at which it's responding is decreased, because instead of responding every 2 messages, it responds every 20 messages. I was thinking about implementing a feature where we could determine which task send which message and that type of thing, but it's not really necessary because we could just use an enum for probably values or just do stuff based on values. So instead of message divided by 20, if the message was 20 or the message was 10 or whatever the case may be, then based on that value, you could perform some task. So this is basically how we implement a queue. It's not really complete yet. Maybe in the next video, I'll try and improve this queue structure. And we'll see how we can implement a better queue system for the microcontroller. That's it, guys. Thanks for watching. Be sure to like, share, and subscribe.